So welcome to the first video on set theory, and my goal for this video series is to make a set of about maybe 10 to 15 videos, hopefully introducing people to set theory, and hopefully providing a nice, concise lecture series on set theory. So in this first video I'll be introducing some common notation that we'll be needing within set theory and a few basic operations that you also need to be familiar with. As with any field of study, we're going to have to start with some common ground, some basic vocabulary that we'll have to all agree on before we start to introduce some more complicated concepts. So what do we mean by a set? So within set theory, we're going to say that a set is a collection of elements or objects. And it's important to note that we're going to take elements and objects in the abstract sense, in the sense that these objects can be numbers, they can be people, they can be motorcycles, they can be just about anything. And we're going to say that a set is a collection of these objects. So an example of a set, let's say set A, could be the numbers 1, 2, 3, and 4 taken as a collection. Or another example is, let's say I have a set B, that's just the Greek letters alpha, beta, and gamma. And remember to take these in the abstract sense, these are just a collection of objects. Now sets may include other sets as their members as well, so you can have sets of sets. So an example of this, let's say set C, has two members. First it has the set 1, 2, has a set containing 1, 2, and a second member, or a second element, is the set containing 3 and 4. So it's important to note here that this set contains two objects, the set 1, 2, and 3, 4, but it doesn't contain four objects. That would be a different set, namely set A, which contains 1, 2, 3, and 4. So within sets, another thing to point out is that there's no order within sets, and that repetition does not matter as well. So if I have the set, let's call it D, being 1, 2, and 3, and the set E, let's say 3, 2, 1, 1, 1, then it turns out these are the same set. Because, remember, order doesn't matter. So 1, 2, 3 is the same thing as saying 3, 2, and 1. And repetition doesn't matter too. So 3, 2, 1, 1, 1 is the same thing as 3, 2, 1, which is also the same thing as 1, 2, 3. So we're going to say that these two sets, D and E, are going to be the same set. At this point, we can introduce some notation. So the first piece of notation I'll introduce is this epsilon-looking symbol, which is often used to show that something is a member of another set. So this thing here, this statement, x epsilon thing A, this should be read as x is a member of A. So whenever you see this thing right here, this proposition, this will mean x is within the set A, or x is a member of the set A. So suppose I have the set A, which has 1, 2, and 3. So the object 2 is within the set A. It lives within the set A. And that will be denoted as such. And 3 is also within A. So suppose I have another set C. So again, this has two elements to it. It has a set 1, 2, and has a set 3, 4. So I can say that the set 1, 2, as a whole, as a whole object, is within the set C. And I can also say the set 3, 4 is within the set C. So my question for you is the object 1 within the set C? Is that statement true? Well, it turns out it's not, because set C only has two objects, as the set 1, 2, and has the 3, 4 object. And 1 is not the same, at least not in set theory, 1 is not the same thing as the object 1, 2. So here's another piece of notation. So we're going to introduce a symbol here, the sideways U with a line underneath it. And this is going to be a relation between A and B. So this whole proposition is going to be read as the set A is a subset of the set B. So what does a subset mean? Well, it means that every object that's in the set A is also an object of the set B. So if X is in A, it's also in B as well. So let's take an example. Let's say A is the set containing 1, 2, and 3. B is the set containing 1, 2, 3, and 4. Now we can notice that every object in A, the 1, the 2, and the 3, is also in the set B, because it has the 1 there, the 2 there, and a 3 there. So the statement every object in A is also in B is true. Therefore we say that A is a subset of B, and we denote that with that symbol there. A is a subset of B. Or we can also say that for all objects in A, such that X is in A, if it is also true that X is in B, then A is a subset of B. And this is the same as before. Just trying to get you guys used to reading the symbols, because that'll become important. And one other thing to note too is that if I have two sets A and B, if A is a subset of B, meaning that every object in A is also in B, and B is a subset of A, meaning that every object in B is also in A, then we say that these are the same set. They're identical to one another. So here's a piece of notation that may be new to some of those watching. So here I'm going to introduce the universal quantifier and the existential quantifier. So the universal quantifier is going to be denoted by this upside down A, and it's often placed next to some symbol, let's say X. And the way to interpret this is going to be, this symbol means for all X, for all objects X. And again, it's important to interpret this in the abstract sense. So the universal quantifier means for all objects X. And correspondingly, we have the existential quantifier. So the way to read this backwards E, is there exists some object X. And again, you should interpret that in the abstract sense. And these two quantifiers are often used in the context of putting some sort of formula or proposition to symbolic form. And oftentimes you'll see parentheses associated with these quantifiers, and these parentheses are going to be read such that. So whenever you see like a set of parentheses, you should read that in your head as such that. So for example, I should read this statement as, there exists an X that lives within the set of natural numbers. So this uppercase N is going to be the set of natural numbers. So you see the parentheses here, such that, and then I read this, X is even. So there exists something within the set of natural numbers where that something is even. And of course that's true, and you can think of lots of examples. Let's say the number 10. Here's another example. So all objects within the set A, so if that's true, that implies that same object is also an A. So of course that's true, that's a tautological statement. But just want to get you guys used to reading these sorts of statements. So here's a practice question for you guys. So what does this statement imply? Well, first let's read this. So on the left-hand side we have, for all x's that live in A, that implies that that same object, X, is also a member of the set B. So where have we seen that before? For all objects in A, those same objects are also in B. So how should we read that statement? Well, remember, that's just the definition of subset, of a set being a subset of another set. So this statement is saying the same thing as A is a subset of B. And yet another way of reading the statement, A is a subset of B, is that for every object X that lives within A, if it's true that that guarantees the truth of that same object being in B, then that implies that A is a subset of B. And notice we have this bidirectional arrow here, so that also means that I can read the statement from right to left, and that should also be true. So A being a subset of B implies this entire left-hand side, that every object in A is also in B. So it's important to just kind of read these statements and kind of understand what they mean. So here's some other notation that everyone's probably familiar with already, but just to make sure. So the ampersand A and B is going to be read as A and B. So I'm sure everyone knew that already. But this other one here, this symbol here, this dash mark, A, is going to be read as not A, or the opposite of A, just the negation of A. And this rightward arrow, which we used in the previous slide, so this is going to be interpreted as A implies B. So what that means is that if A is true, then B is going to be true as well. So the truth of A is going to guarantee the truth of B. So that's what implies means in the logical sense. And the bidirectional arrow is going to be read as A if and only if A, or sorry, A if and only if B. And that also gets written as IFF, so if and only if B. And what this means is that A implies B and B implies A, so you get this bidirectional relationship. So the truth of A guarantees the truth of B, and the truth of B guarantees the truth of A. So that's what the if and only if means. So one thing we'll need too is some way of denoting what sort of objects we're talking about that are going to be included within a set. And one way to do this is to introduce set builder notation. So when we're constructing sets, we can write that down in the following manner. We can say that this new set that we're going to construct, called A, is going to be all objects X, and this bar is going to mean such that, just like the parentheses is going to mean such that. And then what follows that's such that, it's going to be some condition on X. So we're going to say that A is going to be constructed of all the objects where that object is prime, that number is prime, and it's going to be less than 10. So these x's are going to be numbers, and the x's are going to have to be prime, and they're going to have to be less than 10 in order to gain entry into this set. So you can think of this as the statement that has to be true in order for x to be included within the set. And of course, this is pretty obvious what this set is going to end up being. So it's going to be 2, 3, 5, and 7, just those prime numbers that are less than 10. So the abstract way of writing this is that some set A is going to be constructed of all the objects x such that they meet some entry condition. So if they meet that condition, then they get entrance into the set. So one set that we'll be talking about quite a bit is the empty set. So at some point in this video series, we're going to show the existence of an empty set, which we're going to denote by that symbol O with a slash mark through it. So this empty set, it's quite a special set, and its main property is that the empty set is by definition the set with no members in it. So there are no objects within the empty set. But this might seem like a kind of a stupid set or an uninteresting set, but it turns out it has a couple of nice properties. So if A is any arbitrary set, so any set you can think of A, it turns out that the empty set is a subset of the set A. And A can be, as I said, anything you like. So the empty set is going to be a subset of that. And you might be wondering why this is true, but imagine we had to verify that the empty set is a subset of a set A. So how would you do that? So what you do is you would look at all the members of the set A and check to see whether they're in the set A. Or you would check to see whether all the members of the empty set are in the set A. So since there are no members of the empty set, then the statement is vacuously true. And if you're still not convinced by that, ask yourself, could this statement be false? Can you name some member of the empty set which is not an A? And this is something you normally do when you argue that something is not a subset of something else. You would name some member of this set on the left-hand side that is not a member of the set on the right-hand side. So the statement is really only true because it can't be false, or it's vacuously true. Another thing you can do with the empty set is you can form new sets containing the empty set. So I can create some other set, let's call it set A, which contains a set containing the empty set. Or I can create another set, let's call it B, which contains two elements, the first being the empty set, and the second element being the set which contains the empty set. So the empty set is going to be pretty useful in our talk on set theory. So one thing to notice here is that these two new sets I've constructed, A is a subset of B because A contains one element, namely the null set, which is also found in the set B. So A is a subset of B. And also that A, taken as an object in itself, this set containing the null set, is found in B. So A lives within the set B. And it's that second, namely it's that second object there in B. So both of these statements are true. So another thing we'll be dealing with quite a bit is this talk about the power set of a set A. So that's going to be denoted by this fancy P of A. So this is going to be the power set of A. So what is the power set? So the power set is going to be the set containing all of the subsets of A. So you're going to list out for me all of the subsets of A and then put those into a new set. And that's going to be called the power set. So using set builder notation, the power set of A is going to contain everything such that that object X is a subset of A. So that's the entry condition into the power set, that object X has got to be a subset of A. So let's take an example of this. So let's say I had this set just containing 1. We'll call that set A. So what's the power set of that A? So the way to calculate the power set is to list out all of the subsets of A. So let's see if we can do that. So we said in the previous slide that the empty set is a subset of all sets, of any arbitrary set. So that means that the empty set is going to be a subset of A. So that means that it meets the entry condition into the power set. So that means that the empty set is a member of the power set of A. So that's one element in the power set of A. How about the second one? Well, we also know that any arbitrary set is a subset of itself, right? All objects that are in a set are also in that set, so A is a subset of A. So A also meets the entry condition into the power set. So A is also going to be found within the power set of A. And it turns out those are the only two objects that are going to be in the power set of A. So the first object is the empty set, and the second is the set A itself. So the power set of A in this case is going to have two objects in it. It's going to have the empty set and the set containing the number 1. And one useful fact to know about the power set of any set A is that if A has n members, has n objects in it, then the power set of A is going to have 2 to the n members. And we just saw that in this case, A had 1 object in it, namely 1. So the power set of A is going to have 2 objects in it, and we found that here. It had the empty set and the set containing 1. So that's pretty useful to remember when you're dealing with power sets. So we just found the power set of A, which formed a new set, but we can keep going with power sets. We can take power sets of power sets to generate new sets. So on the previous slide, we found that the power set of A was the empty set and the set containing 1. So the question now is, what is the power set of the power set of A? In other words, what do you get when you take the power set of this set that we just found? So we know from the previous slide as well that that since this contains 2 objects in it, that the new power set generated, the power set of A, is going to have 2 squared objects in it. It's going to have 4 objects in it. So we know that the 2 objects already that are going to be common to all power sets is going to be the empty set and that set taken as an entire object that you're taking the power set of. So since we're taking the power set of the power set of A, the power set of A is going to be included within the power set of the power set of A. And that's because the power set of A is a subset of the power set of A, so it gains entry into it. So already we found 2 objects in the power set of the power set of A. So we just have to find the other 2. So one thing to notice as well is that if we take this object here, the set containing 1, this has 1 member in it, which is the set containing 1, which is going to be in the power set of A. And we know it's in the power set of A because it's right there, right? What does this statement mean? That the set containing 1 has all of its members in the power set of A. Well, that means that this whole object here, this whole set here, is a subset of the power set of A. And since it's a subset of the power set of A, it gets included within the power set of the power set of A. So there's our third element of the power set of A. And let's use a similar strategy to find the fourth element. So we're going to look at the elements in the power set of A, and we're just going to throw a set of parentheses around them. So now we have this object. We have the set containing the empty set. Now this has 1 member, which is the empty set, which is also in the power set of A. So all of the objects in this set are also in the power set of A. And that means that this object is a subset of the power set of A. And since it's a subset of the power set of A, it gets included within the power set of the power set of A. So that's going to be our fourth element of the power set of the power set of A. So that means we found all 4 elements of this PPA. So it's the empty set, PA, the set of the set containing 1, and the set containing the empty set. So there are 4 objects. And just to make that substitution at the power set of A, I'm just going to take this whole thing here, the power set of A, and plop it right in there as the second element. So there's the power set of the power set of A. Now, since we're going to be using the power set so much, let's go through that one more time just to make sure that we've understood what we're talking about here. So let's check to make sure all these elements are legitimate, that they're correct to be in the power set of A. So let's take the element, the set of the set containing 1, and we're saying that this object here is within the power set of A. So since it's within the power set of A, that means that same object, the set of 1, is a subset of the power set of A. Now this is just true by virtue of the definition of the power set. So this object here is a subset of the power set of A. Now since it's a subset of the power set of A, that means all objects within this set here are also objects of the power set of A. So that means that the set containing 1 is in the power set of A. And since that object there, the set containing 1, is in the power set of A, that means that's also a subset of A, that same object. Now again, by the same argument we used here, all objects on the left-hand side have to be in the right-hand side. 1 must be in the set A, which is true. That's where we started with our definition of the set A. So we've seen that everything is pretty consistent. You can check this with the other three members of the power set of A. So there are a few other operations that we're going to have to be familiar with when we're talking about set theory. And one of those is the union of sets, taking the union of some sets. So I'm going to introduce this in an informal way in this video, and then we're going to talk about it a little bit more in the next video. So this is probably something everyone's familiar with, taking the union of two sets. Let's call them A and B. So A union B is going to be all those objects X, such that X is in A or X is in B. So if it's that object is in A or if it's in B, it gets to be included within the union of A and B. So just to take an example, suppose we had the set A, which is the set containing 1, and then B is the set containing 1. So we're going to take the union of these two sets. So A union B is going to have two objects in it. It's going to have this thing here, the set containing 1 and 1. So we're just taking all the stuff that's in A and we're joining it to all the stuff that's in B. So that's going to be A union B. So the next operation to deal with is the intersection of sets. And again, everyone's probably familiar with this. So A intersect B is going to be all those X's such that X is in A and X is in B as well. So it's got to be within A and B in order to be included within A intersect B. So again, let's take an example. So let's say C is 1, 2, 3, 4, and D is 3, 4, and 5. So the intuitive notion of intersection is, what do these two sets have in common? What members of these two sets are in common? So you can see the two common elements of the sets are the numbers 3 and 4. So C intersect D is going to have two members. It's going to have the number 3 and the number 4 in it. So hopefully that's pretty intuitive. So the last operation I'll be talking about in this slide is the relative complement. Now, it may sound kind of obscure, but it's going to be very analogous to doing subtracting in the world of sets. So I'm going to denote that as A minus B. Now there are a bunch of notations for this, but I'll be using A minus B. And what this is going to be, this new set A minus B, is going to be all those objects that are in A and they're not in B. So this object, if it's going to be in A minus B, it's got to be in the set A, and it has to not be in the set B. So basically it's going to be all the stuff that's in A with all the stuff that's in B subtracted out of it. Alright, so just to take an example. So let's say we have the set A, which is 1, 2, 3, and 4, and we have the set B, which is 1, 2, and 3. So we're going to take the set A and pull all the stuff that's in B out of it. So we're going to pull the elements 1, 2, and 3 out of it, and what we're going to be left with is just the set containing 4. So A minus B is just going to be 4. And notice that the element 4 is in the set A, so it's an A right there, and it's not in B. So it satisfies the entry condition, so it gets to be included in the set A minus B. So that's pretty much it for this video. So at the ending of every video, I'll have some practice problems, which I've pulled from a number of different textbooks, and maybe some I made up myself, just to make sure you've kind of understood what we've talked about in this video. So here are 4 problems that I think are kind of nice for you to go over, and they kind of relate all the stuff that we've talked about so far. So if you want, then pause the video whenever you want and work on these. And stay tuned for lecture number 2. And also, if you enjoyed the video, thought it was useful, give it a thumbs up, and feel free to subscribe or leave a comment below. Thanks.